Hello again. I hope you had a good rest. Nice cup of coffee or tea or whatever you got. But now we'll continue with Luis Arribas from Spain, from CIEMAT in Spain. And he will present analysis of a collective self-consumption application of a small wind turbine. Luis, please go ahead. You might not be there yet, but hopefully you're on. Yes, good.
Hi, Morten.
Hi, Luis. There you are. Very good.
Hi. Sorry, because I'm at the office now, and someone has started working and making a very loud noise.
Oh.
And I was trying to look for him, but I could not find him.
Yeah. Well, you have to deal with it afterwards.
Yeah.
But anyhow.
I hope
Please
they don't.
go ahead.
Okay, thank you.
Thank you for your participation.
Oh, thank you very much for giving me the opportunity to share with you this work. I will start sharing my screen. Okay, I can.
Yes, it's on now.
Okay. So, hello everyone, and thank you for this opportunity to share with you this work, which is based upon a master thesis made by Sara de la Fuente, which in fact it was planned to be herself the one who presented this work, but it was not possible because she's working in Mexico at the moment on a photovoltaic installation. So I will present the results of this analysis of a collective small wind turbine for self-consumption use. I hope the loud noise doesn't disturb you a lot. And this is the general layout of the presentation. I will start with the background on the situation of small wind turbines in Spain. And after that, I will specify the objective of this work, which will be developed in 3 phases, starting with the description of the case study, and then the design and economical analysis of the installation, and the particular technical analysis we included related with the influence on the voltage of the distribution grid.
Sorry to interrupt you, Luis. Can you speak a bit louder?
Yes, sure. I will
Thank you.
try. And starting with the background of the situation of small wind turbines in Spain, in relation to the regulation, some work was done some years ago for the establishing the procedure to connect the small wind turbines to the grid. And the main goal for a small wind turbine market in Spain for this decade that is ending now was established in the National Renewable Energy Plan for 2011 until 2020, establishing an objective for small wind turbines for the first time, specifically for small wind turbines of 300 megawatts. There was a quite ambitious objective. And in fact, this year, which is the end of this period, we could say that this objective has not been achieved. The reason for this might be found in this same national plan. It was established that for this technology, the small wind technology, financial help was needed in terms of feed-in tariff. But at that time in Spain, there was an abolition of feed-in tariffs for any kind of technology related with renewable energy, and this affected directly to the small wind technology sector. During last years, the regulation for self-consumption has been established, and I will go through that in a moment. But in this national plan, it was some of the main characteristics for the small wind sector were established, splitting the small wind in two ranges, less than 10 kilowatts and from 10 to 100 kilowatts for different applications, and establishing some overall and CAPEX and OPEX costs, which in fact were not the existing conditions at that moment, but were more like a goal to reach for this technology. In relation to the self-consumption regulation, before this regulation, the installed power for renewable energy could not be higher than the contracted power of the user, but this regulation established that this was not, it might be in a different way. I mean, the user might install a higher power even than the contracted power. And established also two different types of installations: individual, which was the existing one previously, and a new one, which was the collective. For this collective type, the net billing was compulsory, and so the user had a different tariff for the energy they purchase than the tariff for the energy they sell. The purchase tariff is accorded with the company, and the sale tariff is accorded with the commercializer. But this net billing could not be negative. I mean, the user would never receive money directly from the energy produced. It was done on a monthly basis, and the distance from the generator to the loads should be less than 500 meters. So this new type was the cause for this work. We liked to analyze this possibility, in particular for small wind. And so we established an energy price and a sellback price. These were established for the general conditions. It depends on the company, on the type of contract, but these figures were established as general conditions for Spain at this moment. So with this background, the objective of this work is precisely to analyze how a shared collective self-consumption facility, in particular with small wind, but not only, we also included solar PV, also to test what it was mentioned in this conference several times, which is the difficulty that small wind has to compete against solar PV nowadays. So this objective is developed in 3 phases. The first one is the definition and characterization of the case study. The second one is the design of the optimum installation, optimum share of solar and wind. And the last point is this particular analysis of the influence on the voltage of the distribution grid. This, each one of these issues will be covered in this presentation. Starting with the description of the case study, precisely because we wanted to analyze the influence of the voltage of the distribution grid, we needed a distribution grid. And it's not so easy to get information on the distribution grid. So we used this European low voltage test case, which is like we could say a test distribution grid, which is public and which is characterized in terms of the disposition, the layout of the grid. In this case is for an example in Europe, so it's 50 Hertz. There is a substation supplying the whole grid, which is in this case is 800 kVA, and the number of users, the number of individual loads is 55. The advantage of using such a grid, such a test grid, is that we could get the information on the lines, on the transformer, of the parameters of the whole grid, and also of the characterization of the 55 individual load profiles. This test distribution grid only includes data for 1 day. So from this 1 day, 55 individual day profiles, we built an aggregate profile for the 55 loads, building this way the daily profile we would use for our design. In the data available for this test grid, there is only information of 1 day. So we, of course, we need data at least for 1 year. So we made the assumption that the consumption was more or less constant throughout the year, in average. And with the random variability, we built a 1 year series. So we had to select the site. Of course, if we wanted the wind option to have some chance, we had to choose a windy site. So we went to the northwest coast of Spain, Galicia, in particular in the north. And well, this was a choice from Sarah. She chose Ortigueira because she had been there. There is a famous Celtic music festival every summer there in Ortigueira, and she liked that place. And also close to Ortigueira, there was a reference meteorological station to provide data. The data for our site that we used was 5.6 meters per second average for wind speed at 10 meters high, which is quite a good place, a windy place, of course. In terms of solar radiation, at least in Spain, it was not such a good place, but well, it's I think maybe a reference for other sites also. And the temperature is quite middle temperature. In terms of the technology, of course, we tried solar PV and Smallwin, but we made a difference between them. For the solar PV installations, we decided to work with distributed individual installations. I mean, using the roofs of the houses to install small PV installations. But for the wind, we changed that way of thinking, and we chose collective use. Only one is a single wind turbine, providing energy to all the users. We thought that, in fact, this choice was quite in accordance with reality, as usually for PV installations, the use of individual ones is quite common. And for a small wind, as you know, and as we will see here, the collective use has some important advantages. So with this case study definition, we went through the design analysis. We used Homer Pro, and we already characterized the grid in terms of the prices of the energy sold to the grid and to the energy with the energy purchased to the grid, and also with the profile of the load. We characterized the resources, and we will characterize now the power technologies. Starting with the small wind characterization, for the cost of the small wind, we wanted the program, the Homer Pro, to optimize the size of the optimal wind turbine. And it's in this sense, we needed a characterization, a curve with the variation of the cost in relation to the power. For this purpose, we used some references, mainly from the American market, and the reference that I showed you before for Spain appearing in the national plan. In blue are the references of the US market, and in pink, the reference for the Spanish market, which is more optimistic, as we really need optimism for a small wind to be included. We chose the pink one, and it's very close to the linear approximation, but it has some reduction of the specific cost as the power increases. And in order to characterize the whole range of small wind turbines with one single power curve, we built a normalized power curve from different power curves from commercial manufacturers. It's an approximation in order to simplify the design process, and we used thinking of a larger wind turbine, a higher tower, in this case of 20 meters. For the solar power installation, well, we will not go much into details, but we chose a standard size, 1.5 kilowatt size for each of the households that would result in the optimal size, with 5 modules and 1.5 inverter. For the cost of the PV, we were not, we chose the pessimistic choice, and nowadays maybe the cost is a bit lower, but it's true that for these small sizes, the cost of PV is not as low as for larger systems. So the results. Before entering the optimal configuration, here I would like to show you some preliminary results in terms of equivalent hours production for solar PV or for wind. In this case, for solar PV in Spain, we could say it's in the lower range, as we suppose. And for the wind, everywhere, I think we would say it's a very, very good windy site. In fact, the equivalent hours that obtained in this simulation more than double the equivalent hours supposed in the national plan. But I would like to remark the generation cost. In fact, somehow I think we built this case study so that the generation cost for both technologies were similar. In fact, you can see that they are quite similar. So the question from this data is what one would expect to be the winning combination, because the generation cost is important, but it's not all. There are other parameters that have influence on the final design. I don't know if this one was your guess, but the optimal solution that we found was a hybrid solution composed of 23 kilowatts of wind power in a single wind turbine and 17.6 kilowatt of solar power composed of distributed individual installations. Here we have the optimal configurations for the hybrid solution, which was the best of all. In the second place, we found the only wind solution. The third place, the only solar solution. And in the fourth place is the existing, we could say, only grid solution. Here I have to point out that what I call the equivalent LCOE includes not only the variable costs of energy, but also the fixed cost of energy. That's why it's higher than the figures I saw at the beginning of the presentation. The results for the winner combination are these ones. Accounting for renewable energy production, it's nearly half of the total energy produced or consumed in the installation. And here we have to consider that not all the energy that is produced by renewable energy is consumed at the same time. So that's why we have the difference between the consumed energy AC primary load, which is the overall consumed energy, and the renewable energy sold to the grid, which is we could say that the excellent energy from renewable energy. As you remember, the price for the energy sold is more or less half the price of the energy consumed, and that's where you get the optimization. In this case, the energy from the wind is nearly 3 times the energy from the solar PV. And in terms of investment, the IRR is more than 80%, and the payback period is nearly 11 years. We could say this would make a reasonable investment profit. Now, going into the technical analysis, in particular to the influence of the voltage, we will use the same configuration, the same analysis we have performed with Homer Pro, but now we will use another software, which is OpenDCS, which is a free software to perform this kind of analysis. We will use the results for the 5 different combinations, and the physical layout of our solution. This is just the remembrance that we are using a collective wind turbine, a single wind turbine, that we placed it on the border of the distribution grid. I think this might be more or less real, which would allow the wind turbine to be separated somehow from the households. But on the other hand, the resulting solar PV installations would be installed on the roof of the houses, so they would be distributed along the distribution grid. Before going into the analysis and the results, just also a background on the norms on voltage influence in applying in Spain, some of them also in Europe. And from, well, I will not go into detail, but from summarizing the results of the analysis of all these norms, we concluded that, as a summary, we could say that the influence on the voltage of the distributed renewable energy production would not be higher than 10% of the nominal voltage, and would not be higher than 2.5% on the transformer output. I mean, there are we could say two limits. One, all over the distribution grid of 10% over the nominal voltage, and at the point of connection to the transformer, to the substation, that the influence would not be larger than 2.5%. So with these limits, we went into 2 types of analysis, one in time and one in space. For this analysis, we selected along the distribution grid 3 points, 1, 2, and 3, which the difference between them mainly is the distance to the substation and also to the generating in terms of the Smallwin. And for the analysis in space, we used 2 particular cases, which is one at the time of the highest wind power supply into the grid, and the other one at the time of the highest consumption. The results are shown in these graphs, Here is the analysis in time for the three locations we marked on the layout. For location 1, which is the closest to the transformer, to the substation, the influence is very low. And as we get apart from the substation, the influence becomes larger. Also because we are getting closer to the wind turbine. In general, we could say that they are within limits, but it's also clear from these graphs that the appearance of the wind generation on the overall installation has a strong influence on the voltage variation, and this influence is stronger as the wind power in the installation is larger, which on the other hand is quite logical. In relation to the analysis in space, here we have in the horizontal axis, we have the distance from the substation in kilometers, and on the left we have the case of the maximum wind generation. In this case, the voltage increase along the distribution grid as we get apart from the point of connection to the substation, and also as we get closer to the generating wind turbine. In the case of the maximum consumption on the right, in this case, the voltage decreases as we move from the substation. But here we can find an interesting effect, which is also should be considered in this future of distributed generation we are going to. That is that the effect of distributed generation, in particular in this case of wind generation, is not always a drawback for the grid. As in this case, we can see that the decrease of the voltage diminishes as we get closer to the wind turbine. So we could say that the wind turbine improves the voltage situation along the distribution grid.
Luis, we have 2-3 minutes more.
Okay, thank you. I am getting to the end. So we could say that within limits, in general, we could say that it's within limits. So of course, it depends on the power we install of wind turbine. So getting to the conclusions, we have to say that it's not easy for a small wind turbine to enter even in a collective use, but the collective use for small wind turbines had some advantages which are important to consider. First, there is a lower specific cost as we increase the power of the wind turbine. This also has the effect to use higher towers, which has the other effect of higher wind resource. There is a reduced space occupation. This is an advantage also against solar PV. And the site selection is easier. It's obvious that it's easier to find a site for just one single wind turbine than for, let's say, 50 wind turbines. Among the drawbacks are the permitting restrictions, which have not been considered. So in some places, there is a permitting restriction of the total height of the wind turbine. That might be a limit for the total power. And as we have seen here in this work, it has a higher impact on the voltage affection of the distribution grid. LCOE is important, but it's not the only thing. I mean, of course, if the LCOE difference is very large, maybe it's decisive. But as we saw in this example, if there should be no such a big difference between LCOEs, of course, that the wind generation might have some chances. And that's all on my side. Thank you. And back to you, Morten.
Thank you very much, Luis. We have a minute or two for short questions and comments. But first of all, very interesting. Thank you very much, Luis.
Thank you.
It's been very nice work you've been doing. Are there any questions or comments? Well, it seems not, so it means that we actually can go on with the next presentation in time. And the next presentation will be the military use of wind turbines by Dr. Galal Osman from Egypt. Are you there, Osman? Galal? I think you are, it seems as you are on your way in. Please unmute. I hope you can hear me, but I cannot hear you. Well, we were trying to send you the request for you to unmute. I hope you got it now. Galal Osman, I hope that you are on. Can you solve the difficulties of being on mute? This is strange, really strange. But in the meantime, well, we have our next presentation will be from Enercon, and that's onshore medium wind. And we are all looking forward to this presentation. I don't know if you, Mikael Månsson, if you are ready already. He's not online yet. So we'll just wait a moment to see. But in the meantime, we can take up if there are any things to be discussed, also about what we have had until now, and or there are other questions to be set up concerning the what has already been said. I can see Mike Berge, you are on. Yeah. Please go on.
I had a question for Louis from his presentation. Louis, you I think correctly pointed out that wind turbine at the end of a feeder can help with the voltage, but it looked to me in your models like you showed that the voltage was the same throughout the distribution network before adding the renewables. Our experience, of course, is that the voltage is reduced the farther you get from the substation, and so therefore the wind systems on the grid always are a benefit because they're always boosting voltage. Sometimes we get into the situation where the voltage is boosted too much and we have to limit the voltage from the power electronics, but that's rare. Did I misread some of the graphs on that?
No, I think you didn't, but if I try to share my screen again, perhaps I can. So because we chose these two, we could say, limit situations. On the left, the maximum wind generation, it means that the balance between the wind generation and the load consumption is maximum, which in general would be a case of very low or nearly zero load consumption. So on the left, there is only increase because there is nearly no consumption from the households. On the right, which is the maximum consumption case, I think this is the case you were talking about. Of course, whenever there is a net load consumption, the voltage decreases along the feeder. But on the left case, really the net balance was not a consumption but a generation. So it's a balance at every moment between the energy that is consumed by the loads and the energy that is produced by the wind or solar PV generators.
Okay, thank you for that clarification. Makes perfect sense.
Okay, thank you.
Are there further questions or comments right now? Well, it doesn't seem, but